A developer needs to format text, so they open VS Code, Microsoft's source code editor, find a highly rated utility extension, and clicks install. There are no error messages or system crashes, but in the background, SSH keys and browser wallet data are extracted. The machine is instantly converted into a proxy node, routing traffic for external criminal networks without the user ever noticing a drop in performance. This data visualization shows the actual scale of the fallout. What starts with a single compromised machine multiplies into a network of 35,800 infected nodes, reaching over 150 distinct open-source repositories on GitHub. The threat actor responsible for this campaign is known as GlassWorm. Their methodology relies on multi-layered invisibility across the software development lifecycle, hiding malicious activity directly inside the utilities developers use to do their jobs. When the basic utilities used to write code are the vehicles stealing credentials, the implicit trust that holds the open-source software ecosystem together breaks down. The attack begins by playing by the rules. The operators upload a completely functional extension to the open-source registry. Because the code is clean, it passes automated security reviews, and developers begin to download it. Days or weeks later, after a user base is established, the attackers push what appears to be a standard version update. This flowchart illustrates the trap of transitive dependencies, secondary packages required to run software. By adding the command extension dependencies, the update links to external malware. The code editor automatically reads this and pulls the malware in the background without any user consent. By hiding the payload in a secondary dependency, the attackers turn the standard software update process into a delivery vehicle, sidestepping the marketplace's perimeter defenses. Getting onto the machine is only the first hurdle. The malware then has to survive inside open-source codebases, where human reviewers and automated security linters are hunting for suspicious code. To bypass them, the attackers use invisible Unicode characters. Unicode is the universal standard for encoding text on computers. Here, the attackers place special zero-width space characters directly inside empty string backticks in the source code. To a human reviewer or a security scanner, those backticks look empty. But when the computer's JavaScript runtime encounters them, a tiny decoder extracts the invisible characters and executes a full malicious script. Armed with access tokens stolen from the initial victims, the malware force pushes this hidden code directly into the default branches of high-profile external projects, infecting widely used Python and React codebases. To ensure these injections blend in, the attackers use large language models, AI systems designed to generate human-like text, to write realistic bug fixes and documentation tweaks as cover for the rogue code. By weaponizing the blank spaces in digital typography, the attackers ensure that visual code review and traditional static analysis fail to detect the threat. When researchers discover a widespread malware campaign, the standard counter is to locate the attacker's command and control server, the central computer directing the infected machines, and shut it down. GlassWorm avoids this by abandoning centralized servers in favor of a decentralized infrastructure hosted on the Solana blockchain, a public distributed cryptographic ledger. Every 5 seconds, the infected machine queries the blockchain network, scanning the memo fields of specific Solana transactions to fetch encrypted instructions. Because this ledger is immutable and distributed, authorities cannot simply seize a server. A delete command simply bounces off the network. By embedding its operational instructions inside a public ledger, the malware achieves a level of persistence that standard defensive playbooks cannot neutralize. Beyond individual victims, GlassWorm functions as an autonomous, self-propagating worm, capable of spreading between systems without any further human intervention. Every time it infects a developer's machine, it harvests their access tokens and uses them to inject itself into the projects they maintain. The victims unknowingly become distributors, poisoning the downstream software supply chain for everyone else. The utilities designed to make coding more efficient, the code formatters, the code linters, and the AI assistants, are the exact tools being used to compromise the developers who rely on them. Securing a codebase now requires moving beyond manual visual inspections. Organizations must implement strict automated dependency audits and deploy specialized scanners designed to detect obfuscated Unicode characters in the build pipeline. The ability to trust an auto-updating development toolchain because it comes from a recognized marketplace has been compromised. Trust in the software supply chain must now be continuously and algorithmically verified.